Hi everyone, welcome to lecture 11. So today we'll be discussing deep learning software. So which involves like PyTorch and like trying to look at some of the features and see how it compares to TensorFlow and so forth. Okay, so before we go into the technical stuff, let's look into some of the administrative stuff. So project 2 is due today. So I'm hoping like people are crunching to get it done. So I'll try to finish today's lecture faster. So yeah, so good luck with that. And project 3 will be out tonight, and it's going to be due on March 14th. Some notes on final project. So these are the tasks again that we have for the final project. So the first portion of that, which is actually about the project proposal. So here are some recommendations from my side. I know some of you like probably did not have time to think about like what is the topic of your interest and like kind of narrow down your paper that you want to implement as a team. So I would recommend each of the team member to read a paper in the topic from the list of papers that we have in the website, and make time to meet with the team, like either in person or Zoom, discuss your notes, kind of own a particular paper that you are reading, so that each member is reading different papers and then you're sharing and talking about it. And then try to select a paper that you all want to work on so that you can reproduce and extend on top of it. So these are some recommendations I have because you want to select the papers by this Friday. So I'm trying to impose these deadlines so that we kind of progress, in a regular interval, so that we are not looking at everything at the end. So I think this will not be graded, but I would highly recommend having your paper selection done by Friday, unless you have some issues figuring it out. So a Google form will be sent out soon for doing that. And then you have your final project proposal, which will be due next week on 2nd. A template for that will be sent out. The template will have the sections, subsections that I like you to write, and also like try to think about it as a team. So we know what are we reproducing, how are you going to evaluate each other, and also like what can we expect at the end of the semester. So yeah, so that's about kind of deciding what your final project is going to be. The other aspect is student lecture presentations. So this is going to be lectures done by the teams that I sent out yesterday on the Canvas. So the first presentation for that would be on next week, which is 2nd of March. I would like the teams to meet with me the previous week, at least to give a week of time, so we can talk about what are the topics you need to cover in your lecture, and also kind of have an outline of your slides. So then you can work on the details and make sure you have enough material to cover for the entire lecture. So these lectures will be like roughly around 45 to 1 hour, because like each team will take one particular portion of lecture. So we want to have enough material to cover. I know I think one team has 2 members, so I will be supplementing some material there. I think that's the first team who's going to go on 2nd. So if your presentation is on Tuesday, meet with me during the office hours the previous Wednesday. So we have 1 week of time for you to work on your slides. Same thing, if you are presenting on a Thursday, you want to meet with me on the previous Friday during my office hours. I will be sending out reminders to each of the teams so that we can figure it out. Okay. So with that, I will let Baha Aldeep to share his screen. He's going to talk about how to use MSI, the Minnesota Supercomputing Institute's cluster. So if you should have already received your account details from me, like I sent that like last month. If not, like try to search in your email box for MSI. I think you should have an account. And yeah, Baha is going to give you some brief tutorial on how to use it, how to access the nodes and stuff. So let me stop sharing the screen now.
All right. So hello, everyone. My name is Baha Aldib. I showed up in your class with Spot initially. And today I'm just going to be taking a few minutes to introduce you to MSI. I'll be giving this presentation. It's not an extensive presentation. It's the goal of this presentation is to give you a summary and allow you to quickly start using MSI. I don't know if Karthik shared these specific notes, but we'll if you find these helpful or would like to get access to them, we could forward more details, or you could ask questions. Also, please stop me and ask questions whenever. This is not a very structured and rigid presentation. Anything that's confusing, please ask. So again, by the end of these notes, I hope that you will have enough details to be able to access MSI interactively, specifically the powerful compute units that MSI offers, with the goal that to allow you to use GPUs and be able to develop and train your models for the class. One note here is that to access MSI, you have to be either on the University of Minnesota network, or either directly or through a VPN. So either you'd be at the university accessing the internet or have a VPN connection to the university. I'll be using such terms as VPN. I assume you've bumped into them. If you haven't, the terms I'm using can be easily Googled, and you can learn about them online.
So Baha, can I add something before you go on? So if people are wondering why we are talking about MSI at this point, is I know some of you guys are already trying to start on working on your final project. So this is going to be your a computing infrastructure that we provide for this course. Yeah.
Mm-hmm. Yeah, thank you. Yeah, exactly. So you'll get a sense of what the MSI is and what it offers throughout this. Before I dive into a demo, which I'll be using this video as a demo, but before I dive into that, I want to highlight that MSI is a large resource. It stands for Minnesota Supercompute Institute, and we're only going to be looking at a minor portion of it that might get you up and running, but please refer to their website for more details. The website is msi.umn.edu, and they have a lot of tutorials and details on what they can offer. So for the sake of our presentation today, we care about the high process computing resources that MSI offers. And you can picture these as, let's think of them as a house, as a building with multiple rooms. That building offers very powerful resources for us to use, including high-speed networking, high-performance storage, GPUs, and large memory computers. It offers all of these, and you might want to access whatever you find necessary for your project. So I described it as a house because these resources are not off the bat offered. This house has multiple rooms, and each room has its own abilities. So currently, HPC has 3 systems. Again, each system has its own strengths and weaknesses, or even its own versions of GPUs, etc. I scatter links throughout this this presentation for you to get a sense of where to go to check out more details. So this is the MSI website, and briefly, I just want to highlight that In their presentation of HPC, they mentioned that, hey, we have these resources. And by the way, Mangi, that system, offers, for example, NVIDIA V100 GPUs. These GPUs might be incompatible to what you're trying to run. So you could, if you find that that is the case, you could go to Agate, which offers NVIDIA A400 or A40 GPUs. So you could get more details about what they offer through the website. To access these resources, you have to have a principal investigator, which in this case is Karthik and I, and we already gave you access to the resources. There are multiple ways of accessing those resources. You could just execute code on the servers without interacting with them, but because I imagine it might be easiest for everyone to start by interactively working with them, I'm going to present on how to access them interactively. There are multiple ways. This link shows you a list of ways to do so. One that I thought would be easiest for most is the desktop. So again, I won't be going through and accessing this desktop right now, but if you navigate to the MSI website, you will be able to find, actually, I will go there to demonstrate. I believe it's under services and interactive access. You'll find a presentation and you'll find a list of links of all the interactive ways, all the ways to interact with the servers. One of them is on demand, which provides you with the ability to access user interface or access a user interface for different applications. So in this example that I'm going through, I went to that link, and I'm showing here the list of interfaces that they offer. You can access a desktop. I access here an Agate desktop. So again, I went to the Agate room. I asked Agate for a computer with an interactive GPU, and which contains 16 cores, 60 gigabytes of memory, etc. And I set the time to 5 minutes because it was only a demonstration. Be aware that the way that MSI allows everyone to access these computes is by giving them different priorities. So if you start using your computer and you always access your computer for hours and hours, and other people have not gotten the chance to access, you will start getting less of a priority to get these resources. Meaning, maybe you've accessed it for many hours and you come again to start a desktop. Someone who has never accessed it will get a desktop before you do. So keep that in mind. And in this case, I open my desktop, and here I open a terminal to show you that we in fact have access to a GPU on this desktop. This desktop also has basic code editors you can open and code. Note that this might not be the quickest way to code because there are delays because of the visual interaction with the system. So you might want to code separately and use this to run or debug or etc. Again, this is only one way to access the resources interactively, and I'm going to be using the demo to demonstrate a different way to access it. So actually, before I start with the demo, this method is called an interactive srun query. The MSI system uses something called Slurm, which you can Google. It's a common software to manage servers, server resources. So you could use these srun commands to ask Slurm to give you certain resources to certain compute. I'll jump right in. In this case, in this demo, I used the terminal to access the MSI. And actually, I'll go back and pause for a second. In this example, I accessed MSI. So this is a detail for those who decide to get access through the terminal. Before you get to the high compute units, you have to access the MSI house, right? So you have to get through the front gate. And to do so, you have to SSH into the MSI servers. Again, for those who are not familiar with SSH, please look it up. It's a common tool. So in this example, I will SSH into MSI. This is how you do so. I will request resources, and I will demonstrate how to get software loaded onto these resources and then run a piece of code. So for those who are familiar with the SSH, the -y informs SSH that I want to interact and like display visuals or forward visuals from the computer to my screen. Here it asks me to validate, like verify who I am, and we are in. So now we are on the MSI server. I then use the srun command that I mentioned, and for details on the flags that srun can take, you could also consult the internet or the MSI website. So in this case, I'm asking for one computer for 15 minutes, and I want this partition to be an interactive GPU. And I will go back and mention that again. Again, I tell MSI that I want X-X11, which tells it that I want visuals forwarded. And here, notice, again, I verify that I do have access to a GPU. So before I continue, any questions? Because that's a lot for someone who hasn't done it before. All right. Stop me if you think of any questions. Okay, so I mentioned that we need to load software. So again, when you're on this system, you are not an administrator. So you will not be able to use apt-get or apt-install for those familiar with Linux. You won't be able to download and install software. Instead, you could use this module command. And MSI has a set of softwares that it can support. Here I use the avail module avail to show that, hey, they have these CUDA softwares available. And for those familiar with GPUs, CUDA is necessary for us to use GPU resources. So here I load the CUDA 11.2 module. And because I like using Conda or Anaconda to manage my Python packages, I also load an Anaconda module. So for the purpose of this presentation, this is all I need to load. Obviously, there are many more modules available. Also, for the sake of time, I had already set up the environment with the code I need or with the software I need to demonstrate. So again, I use Conda to list my, I'm asking basically Conda to tell me, hey, what are the environments available? And it shows that there's this py36-torch-env, which has my Python libraries installed. I use source to activate that. And now I have my Python libraries. So to verify that, I open Python, interactively, and it shows that there's Python 3.6. So I can run 3.6 Python code. All right, now let's write some code. Even better, let's have the now infamous ChatGPT write us some code so that we can demonstrate that GPU works. So here I asked ChatGPT to give me an MNIST piece of code or a piece of code that trains on the MNIST dataset to classify numbers. And obviously it's sped up, but we got this piece of code. Touch is a command that allows me to create a file. So I'm creating a file called MNIST classification. And I will just open that file here and paste all the code that that was given. Granted, for those who are curious, I did edit the code slightly. So if you go back, you will not see that, you will see that it's not the same code, but well, here we go. And now I'm just gonna run the code, downloads the data set, and whoops, I have an issue. So there's some issue with selecting the device. Remember, we had one GPU in this scenario. So going back, notice that there's a CUDA 1 device, which is, for those familiar, also CUDA 0 is the first GPU. So there's no CUDA 1 for us. We save and we try again. All right. Should take a minute. We train for, in this case, 5 epochs. For those familiar also, MNIST dataset is quite basic, given today's compute resources and today's libraries. So 5 epochs prove sufficient for us to finish training. We test it out and we get an accuracy of 99%. Sorry, I hide it. But here I also demonstrate that I'm able to display an image and see it on a window. And we are done. Again, check out the MSI website for more details. So this is the main demo I wanted to give. I should have included this as a note, but I will mention that you could use Visual Studio Code to SSH into the MSI server. And if you do so, you'll be able to more easily develop and code. For more on that, you could probably look it up online. You'll find resources if you type remote SSH via VS Code. But for now, that's all I have. And if anyone has any questions, please go ahead. Otherwise, I'll give it back to Karthik.
Any questions from anyone before I steal the screen?
So Baha, thanks for the presentation. Just one question. So if your team wants to work with the same data, is there like a certain, I'm guessing there's a way where you can download it all to the same place such that everyone can keep accessing it. Is that something you have experience in?
Yeah, so I don't have an answer right off the bat. I know it exists. I urge you to check out MSI for shared storage, right?
Okay.
I
guess my question had more to, I saw somewhere there's like some limit of like 150 gigs. Is that gigabytes? Is that just for a certain type of data storage, or is that all we get?
That is initially what you get. Okay. If you need more, you could certainly ask for more if you can justify it. 150 gigs is a lot to start, but also there are other, I know from, in general, in these systems, there are other places where you can store temporary data that can be accessible by multiple people. Okay. So I can get back, but I also urge you to check out the website or reach out to MSI. Otherwise, I can do that myself. And just to reiterate on that, if you find that your project needs more than 250 gigs, we can justify likely getting a little more data storage.
Okay. Yep. Sounds good. Thank you.
Yeah, no problem.
I think there were a couple of questions on the chat. Somebody's unmuted. Okay.
Let's see. Yeah, about sharing the document, Karthik, do you intend to share this or?
Yes, I think we can share this. So after this lecture, we will make sure that we'll put the link on the web page so you can have the access to this document.
So to answer another question on the chat, again, there are multiple ways to upload data to MSI. The website has details on that. I don't know them off the top of my head. But yes, if you're using code, certainly use Git. It's a tool that you should get familiar with. And otherwise, if the data is not local, if it's online, there are multiple command line methods to download data from a website or from a link. Sorry. So there's wget, for example. There you could also there was a response suggesting SCP. You could also SCP over SSH, another thing that you could look up. So whoever's interested, take note. You could you could, with knowledge of the IP, with a little knowledge of SSH, if you look up SCP over SSH, you'll be able to transfer files through that. So about installing packages, there was another question asking if you can use pip or conda. The answer is yes. What you can't install is Linux software. Python pieces of code are stored in a folder locally, so you could use pip or conda, but I'm not sure if by default Python is available. So that's an example of something you could use the module command to load up. Does this answer questions, or is it still vague?
So first of all, thank you, Bahas. Thank you so much for doing this. I would say, like, if people are interested in, or if they need computing resources, they should get started on MSI. At least check out like how you can run, let's say, the MNIST demo that Baha was showing. So make sure at least maybe you can run your project one or something on the MSI, so you're comfortable with the available resources. And if you are not, let's say if you need more resources, if you need more memory, more stuff, I think you should let us know earlier so we can tweak your final project accordingly rather than waiting towards the end. That's what I would recommend. Okay, so to give a recap what we discussed in the previous lectures, where like we talked about activation functions, data preprocessing, weight initialization, regularization, followed by what we called training dynamics. We looked at how the learning rate schedules look like, and also like some rule of thumbs to actually start training your neural network. Okay, so in terms of frameworks for doing deep learning, so there are many, and I think each of them have their own benefits. For instance, there is Caffe, which later translated to Caffe 2 by Facebook. And also there are other frameworks which are more on C++ based. For instance, Darknet, I think it's based off of C++. And also, like, depending on which company, they have their own frameworks. For instance, Google has Zax, Baidu has something called Paddle, and Amazon has its own MXNet, and so forth. And more importantly, I think more predominant frameworks are basically PyTorch and TensorFlow. So we'll just focus on these two. But trying to give a snapshot of, like, there are many frameworks, and depending on application, whether you're focused on hardware accelerators or you're interested in prototyping, I think people tend to use different frameworks. So if you recall, we talked about computational graphs during backpropagation, right? I think this is probably the so these frameworks basically provide huge benefits for doing or having these data structures called computational graphs, so you can do automatic backpropagation. So some of the motivations to have these deep learning frameworks is that one is they want to allow developers or people who are doing research to do rapid prototyping of new ideas, so they don't get bogged down by computing gradients or like trying to um, work out on how to come up with gradients for new loss functions and so forth. So the second one is also kind of intertwined with the first one, where the automatic computing of gradients is essentially super beneficial when you are prototyping new ideas. So so 1 and 2 basically talks about how easily can you structure your neural networks and also compute gradients. And the third aspect, or the third motivation to have these frameworks is that you want it all to be running on GPU, CPU, or tensor processing unit, which are TPUs specifically for running deep learning networks. And you don't want to get bogged down by this. Like, you don't want to think about low-level compute and how these operations are being done on these hardware accelerators. So yeah, I think this is the main motivation and advantage of using deep learning frameworks. And in fact, I think with these frameworks, we have come a long way in prototyping and trying to come up with new architectures and be very productive in training new architectures. Okay, so with that, let's dive into some of the features of PyTorch. So for this class, we are using PyTorch version 1.13. This was released last October. While you're looking for the final projects, you might be looking into papers that are a little older. So be careful about the versions of PyTorch that your projects are using. Like if there is a code available for some of the papers that you're looking into, try to keep back of your mind that some of the APIs have changed quite a bit before it got standardized after 1.0. While we're talking about versions, just a quick note on the fact that PyTorch version 2.0 is going to be released soon. Apparently, this has got much more optimization with what they call this feature called torch.compile. And one other aspect of this is they wanted to make it backward compatible. And so what is happening in the space is that, with Moore's law, that hardwares are getting better and better. So your GPUs are getting faster. They're also getting cheaper, which means researchers or people who are actually trying to build these neural network architectures are building complex models, and it's getting complex and complex because they are able to access more GPU power. So they are able to realize their designs and trying to work with them. And now there is also a third party which is trying to build up these frameworks. So we can call them API developers. So they have to make sure they are catering to these demands, right? Like they need to make sure the APIs are good enough to access the hardware accelerators, at the same time providing the flexibility to people who are doing who are coming up with these crazy neural network models. So I think all these three parties, one is on the hardware side, the other one on the design of network architectures, and the API developers. I think they kind of work in tandem to make this possible. And I think we'll see some really cool versions coming up in real soon in the future. Okay, so some of the fundamental concepts to think about and to kind of appreciate, to be honest, with PyTorch is the fact that you have these three things. One is tensor, the other one is autograd feature, and also the feature of having modules. So tensor, I mean, you're already exposed to this with project 0, 1, and 2, where it's basically a NumPy array, but it can run on GPUs. So imagine you're not thinking. So when you're using these sensors, you're not talking about like how these operations are going to happen for these sensors, because those things are automatically built it up for you. So that is one of the feature of PyTorch. And AutoGrad and modules, which you will see in the project 3, 4, and also maybe in your final project, it talks about how does PyTorch build these data structures, these computational graphs out of the tensors, and can compute the gradients automatically. And modules let you construct more complex neural network architectures. For one simple example is you saw residual networks. So there is a residual block that is being like copied over many times, right? Like, so imagine having a module would make your prototyping so much easier, and you can think about creating much more complex architectures in a very simple fashion. Okay, so to kind of understand the benefits of these 3 fundamental concepts, let's take a running example where we want to train a two-layer fully connected network with ReLU activations and an L2 loss. So, I mean, this code should be familiar at this point, right? So we have some random tensors where we're talking about values such as what is the number of samples in the batch, what is the data input, what is the hidden variable, what is the size of the hidden variable, and what is the output size. And then we have X, Y, W1, W2, where W1 and W2 are talking about your 2 layers. And these are the weight parameters that you want to learn. There's a forward pass. So for each of the training iteration or the optimization step, you are doing a forward pass. You're computing the hidden vector, and you're clamping for the ReLU activation, and then you're doing matrix multiplication and computing the loss, and then followed by computing the gradients. So you did this manually for your previous project. So you know that this is a backward pass, and then you update your weight matrices or by using this gradient step. So this should be familiar, right? Like we have seen this in different fashion over and over again at this point. So one thing that you might already be like thinking about, or you might already have encountered, is the fact that we can select the device on which you want to run this, right? And the PyTorch actually makes it super easy. All you have to do is basically specify which device that you want to store these tensors and do these operations. And this is a very good feature, because then you don't actually have to deal with the low-level details of how these computing is actually happening. So this is like actually given out for you by PyTorch. The other feature that we kind of mentioned about is the AutoGrad. So if you actually say that for these tensors, you want to have this AutoGrad feature, for instance, X and Y, they are input and output. So you don't need to store the gradients. Whereas for W1 and W2, that's where you want to have the gradients, right? Like you want to store the gradients for these tensors. So you can just have this flag that says requires grad. Then PyTorch actually stores that information during the forward pass and can do the auto grad for you. So once you have this, so the earlier code is kind of simplified now. So you don't have to do the gradient computation by yourself in an analytical way. All you can just do is like loss.backward, and it does compute gradients with respect to all the inputs that have this particular flag true. Right, so if I go back, this is what you had in the previous like when you were computing the gradients. But now when you use the AutoGrad feature, all that is falling into this line that says loss.backward. So if you look at what is happening during the forward pass has not changed, right? Like, but because you have this AutoGrad feature during the forward pass, what's happening is you are building up the computational graph step by step. So you have matrix multiplication of X with W1. So your computation graph is is building up as shown on the left side of the slide. Then you're clamping it, you're actually using ReLU to do this, and followed by a matrix multiplication. And then you're computing the loss. So there is this operation of figuring out how close you are to the ground truth labels. And then you have, this is an L2 loss, so you have squared sum of the same thing. So the summation is happening for all the elements in your batch. So now when you say loss.backward, the PyTorch uses this computational graph that was built during the forward pass and computes the gradient for W1 and W2. Once it is done with the loss.backward line of operation, the thing that happens with AutoGrad is your computational graph is kind of destroyed. So it computes W1.grad and W2.grad, which you can use later, but the graph itself is kind of eliminated at this point. Now you can use these W1.grad and W2.grad to update your weights. And the thing to note is you want to make sure that you are setting your gradients to 0 after the update. So you don't want to have the influence of this particular value in your next optimization step or next training step. If you already noticed, there is this torch.no_grad. So this basically says that for the steps that are following, which is W1, you're updating W1 and W2, you don't want to build computational graph, because if you don't have this particular clause, it's going to build the computational graph for every step. I'll stop here and see if anybody has any questions so far. Is that clear? Okay, so we saw how we can have AutoGrad. So you don't actually have to compute gradients for yourself, which is what you'll do for the later projects now. And the advantages at this point is you can just say loss.backward and it does the gradients for you. And the thing to note is when the gradients are computed, once you have the accumulated values on these variables, your computational graph is cleared out or destroyed. So it builds up in the next iteration. So for the next iteration of the for loop, it builds up the computational graph. So we'll see some discussions about that in a few slides now. Okay, so you can also write new functions. For instance, instead of having to write all of this separately, you can also say, okay, I'm going to define a function called sigmoid, and I'm going to do this operation on the values after x is being multiplied with W1. So what happens here when you define this function separately is the same thing. So it's going to build a computational graph once it hits this particular step in your code. So it's building up this entire graph to do the sigmoid function. And similar to what we saw earlier, when you come back and say loss.backward, it's going to compute the gradients for W1 and W2. You can also define what we call AutoGrad operations on a particular function. This is subclassing the function with forward and backward step. So we saw an example of this earlier as well in the previous lecture, but here you are defining a particular function that has the forward and backward operation. So here it is sigmoid function. So on the left side, what you're seeing is it's basically a Python function, whereas on the right side, you are building this new AutoGrad operation so that there is a forward and backward function inside. So the simple difference between the left and the right is on the right side, your computational graph is going to look like this. So instead of all the steps for a sigmoid function, it's going to just like load this sigmoid function that was already defined as an AutoGrad operation. So I think this will be useful if you're coming up with new loss functions. But in practice, I think addition of this is not going to have too much computational brain. So I think existing, like just using Python functions should be good enough, unless you want to like you are using like much more complex loss function, and you want to have this particular particular way of defining an autograd operations on that. Okay, so one other thing that that PyTorch has is what is called a neural network module. It's called NN. And this basically has higher level wrappers. And it just makes your code pretty and like simple and easy to use. For instance, if you have multiple blocks, you can actually create a block, for instance, model here that has the 2-layer linear layers that we were talking about earlier. So you can have hyperparameters that are defined for this particular block. So here we have this 2 sequence, like one is a linear layer followed by ReLU and then followed by linear. So the idea here is that this acts more like your object-oriented API. So you are basically leading towards or inclining towards building like much more complex neural networks, and this makes it easier to look into your code, write your code, and also debug your code. So once you have, let's say, this is for the 2-layer neural network that we are taking as a running example. So now your forward pass is just this one line of code that uses the model with an input X. And the NN module also has loss functions. So you can have some helper functions on predefined losses that you can use, just like what is shown in the slide. So now we have prediction followed by loss. The next step would be using the loss.backward. So again, this is going to use all the model weights that you defined in your sequential block, for which the required grad flag is already set into true. Okay, so again, once you've computed gradients, you need to update your weight parameters, right? So here, if you use these sequential modules, you can just like run through all the parameters inside the model parameters, and then say, okay, update the parameter with its gradient. So it's as simple as just using this for loop, than thinking about, for instance, if you had like many layers, you don't want to do for W1, W2, W3, and so forth separately. So this is very concise enough to say, okay, for all the model parameters, just update update the parameters with its gradients. And again, you want to have the model.0 grad, so you don't carry forward the gradients to the next iteration. So is it clear? Like we are like trying to progress towards writing the code in a very simple way, than thinking about all the individual steps, so that we can progress towards like building up more complex and more think about like prototyping much bigger and much complex neural networks. Okay, so now one other thing that you can add is using optimizer functions. For instance, optim module that PyTorch has can take in the model parameters along with your learning rate, and it removes the additional steps that you had from the previous code. So previously you had this for loop where you had to make sure that torch.noGrad is used when you're updating your parameters. So you don't actually, by mistake, have a computational graph built up for that. So you can avoid all those things if you're using torch.optim. So here in this specific example, we are taking Adam as an optimizer, and it takes in the model parameters along with learning rate and creates this object called optimizer. And the optimizer, later on, you can just say, okay, dot step. So it updates all the parameters in your model. And then you can call the 0 grad so you don't carry forward. So you can imagine that the code is getting much simpler at this point. right? Okay, I'll stop here and see if there are any questions so far. Okay. So I think the other way to think about it is like you can also define new modules. For instance, here you are creating your own module that composes the entire 2-layer neural network that we have been using as an example. So so it has an initializing function. If you are familiar with Python, you should be familiar with this. So the initializers kind of sets up your children, or if you have any other modules. For instance, the other modules that we are using here are the linear blocks. And it also has a forward pass. So forward pass is something that you'll have to define. You don't have to define the backward pass, because once the forward pass is done, the computation graph is built up and it automatically does your backward pass. So the advantage of using these like your own neural network blocks is, for instance, let's say you define something called parallel block and you want to use that in your architecture repeatedly. So you can just call that module in your sequential block. So the way it would look like is, for instance, if you have a parallel block that looks like this, but you wanted to like stack it over and over again, so you can just like repeatedly call your own module that you instantiated. So this might look familiar to what we saw in the previous lectures on the residual blocks. So if you have a residual block that you define, you can call them, you can instantiate that and stack it for your neural network. And similar to inception module, let's say in GoogleNet that we saw. So you can just define one particular module and then repeatedly instantiate that and like create your own neural network. And behind the scenes, PyTorch takes care of like the model parameters and trying to store the values during your forward pass and then do the backward pass for you. So this is awesome, right? Like, so you can start building up like much more complex neural networks and think about more of your task than getting bogged down by the implementation details in building up neural networks. So one other thing that you might see for your final project is using what we call data loader. So there are two things here. One is the data loader function itself, and the other one is dataset. So the dataset is the one that that loads the data from your hard disk. Whereas data loader, it kind of manages your batching, shuffling while you're training your network. So I think by default, you could probably try to use a tensor dataset, which is a simple one from PyTorch. But sometimes you might want to write your own data loaders that can take your custom data and try to use that for your project. So you might see data loaders for all the projects that you're looking into in your final project, where you might want to think about like how to use them or like understand how the data loaders work. So in this specific example, what is happening is, so you are looping through the loader at every training step. And what this does is it is going to call the tensor dataset module, and that's going to load the data from the hard disk. So in a way, for every iteration, it's kind of loading the data from the hard disk, especially if you're looking at ImageNet, which has so much data, you don't want to load that ahead of time. You want to do that like over the training iteration, especially in the form of mini batches. So data loaders is something to look into and also like maybe play around and understand how to use that. Okay, so more recently, I think PyTorch has also been coming up with standardization of some of these networks. So for instance, AlexNet, VGG16, ResNet 101, So you have these pre-trained modules available in this library called Torch Vision, which is actually from PyTorch. And I know for a fact that there is also transformers nowadays that you can use off the shelf from PyTorch. So while you're using more recent networks, I would say be careful. It might not be too customized. For instance, when I was trying to use VID transformers like a couple of years back, it was not standardized on PyTorch Vision, especially for image input. So you want to like make sure you understand how they're using it, but most of these are standardized before they are released. So yeah, right now you can just use AlexNet off the shelf with pre-trained weights. So which means it's already trained on ImageNet, and you can just use that weights for fine tuning for your specific task. So if this is something interesting to you, I think you might want to start playing with this. So you already have the props data set, right? So you can try to play around with AlexNet, VGG16, ResNet, and even like maybe come up with accuracies for the props data set, just like what we saw for ImageNet classification. Okay, so we kind of hinted on what we mean by dynamic computation graphs. So why do we call it dynamic? So for instance, you are creating the tensor objects, but then at every iteration, when you do the forward pass, your computational graph is getting built up. But then once you get to the stage where you're doing the backward pass, once the backward pass is done, your entire computation graph is kind of thrown, like it's destroyed, right? So again, if it goes to the next iteration, your computation graph is getting built, and you're computing a loss, and then you're doing the backward pass, and it gets thrown away at this point, right? So I think you might want to think about like, why is this happening? What is the use of like throwing away at every iteration? The idea behind doing this is that you want to have some sort of control flow, so that depending on the previous loss, let's say you want to define a new set of weights for it to update, you want to throw away the previous computation graph and build a new computation graph. So to kind of sink in, here is an example which has two different weight matrices for your second layer in a two-layer example that we were looking at. And we can also have an if and else that says, okay, if the previous loss, so we are tracking the previous loss, and if the previous loss is less than 5, we are going to use W2A instead of W2B. So now imagine for every iteration, depending on the previous loss, your computational graph is going to be different. And there are reasons why this is very useful. So I'll show you some examples later. But it is kind of obvious, like, to have static graphs, because then you can be computationally much more efficient. So PyTorch actually offers this. So for instance, you can actually have a model and then say, build a graph before even starting your training. So you see that this graph, and JIT is basically just-in-time compilation. What it does is it builds up the graph before you start your training. The training actually starts in your for loop, right? Like before you start your training, you are building up this graph, and then you're saying, okay, now I'm just going to use this graph for training. So this is more of a static graph and not a dynamic graph. So you can also make it with some control. Like for instance, in this example, there is an if and else condition, but you are kind of creating this graph ahead of time and using it in this particular object called graph, and you're going to use that. So you can actually build up the control flow earlier as well. Okay. Any questions so far? Okay. So yeah, so you can also do this trick of like having an annotation that makes it easier. But the idea of static and versus using static graphs is that when you have static graphs, your framework can optimize it much more. For instance, instead of using convolution followed by ReLU, you can have fused operations, and this is more on the side of low-level features, so to make it very efficient if you're like thinking about deploying it and stuff. Okay. So yeah, so I think again we are talking about the same thing here. The static graph sometimes can be hard to debug, whereas your dynamic graph is basically using the code that you're writing, whereas in static you're doing some sort of compilation. So we do not know what is resulting in a particular runtime error if you are not able to, if you are using a static graph based optimization. And there are like very interesting papers that came out which uses this feature of dynamic graphs. For instance, if your input changes and you want to use, depending on your loss functions, you want to add a few more modules to your graph structure, then I think by using dynamic graphs, you can actually modify the number of layers in your network when you're doing backpropagation. So some of the interesting examples here are you looking at differentiable algorithms for particle filters or Bayesian inference, where your network kind of changes dynamically based off of the output or the loss that you're computing. Okay, so some of the examples are like basically recurrent networks, recursive networks, and modular networks. Maybe even the network that you're using for your final project. Okay, so far we talked about the features of PyTorch. We talked about tensors. We talked about the autograd feature and the ability to use modules such as NN, Optim, and so forth. And we also talked about like what could be a static graph and what is a dynamic graph. I'm not going to go into the details of the TensorFlow. The one thing that you might want to learn about TensorFlow is that in opposite to PyTorch, TensorFlow, the default is the static graphs. In PyTorch, the default was, the default is dynamic graph. And then TensorFlow, now they're trying to move towards dynamic graphs, whereas PyTorch is trying to move towards static graph. So they're like trying to like come together in one way. So I'm going to leave these slides here because we are not going to use TensorFlow for these projects unless you have your final project on TensorFlow and if you're familiar with it. So I'm going to like push through this and then kind of give you the summary. Oh, and yeah, before going to the summary, there is also this feature called TensorBoard that I would highly recommend learning how to use this, because you can log your data. So it's basically used for logging your training. You can record your loss. You can have some statistics that you want to see. You can also look at gradients and how they are changing over a period of time. You can also inspect each of the layers in your neural network separately, and it basically gives you some pretty graphs, and you can also see outputs at during the validation time as well. I think I also mentioned like there is also WNV that people commonly use these days. So I think it's a choice of the designer or the developer to think about whether you want to use TensorBoard or WNV for doing this. I think the TensorBoard is probably more simpler and easier to use, whereas WNV kind of gives you more options. And it's more customizable, and you can track much more information with WNV. Okay, so the TensorBoard is not restricted to TensorFlow. You can also use it with PyTorch. So it's easily usable. Okay, so basically the difference between PyTorch and TensorFlow is that TensorFlow is static by default, whereas PyTorch is dynamic by default, and they use JIT that allows for static graphs. What else? Yeah, I think mostly the academic circles, they tend to focus more on PyTorch, because TensorFlow, I think you would probably want to use that if you're trying to standardize and make sure you go into production with that. Yeah, so that gets to the end of today's lecture. So we talked about some of the features in PyTorch, then we talked about static graphs versus dynamic graphs, and a little bit of comparison between PyTorch and TensorFlow. And in the next lecture, we'll talk about object detectors. We'll talk about RCNN, fast RCNN, faster RCNN. So that is the end of today's lecture. I'm going to stay here if you have any questions that I can help with.